people. Okay. Oh, people are still coming. Guess it's time. Okay, let's start. So this time we'll go over this 1.4 and 1.5, where I guess can I jump? So in 1.4 we talk about those elementary matrices. So elementary matrices, you apply row operation on the identity matrix. Then you can get oh, never mind. And yeah, anyway, we talk about elementary matrices, and they are matrices. Basically, they do row operation. So if you if you apply the row operation on the identity matrix, then the matrix you get is a corresponding elementary matrix. And then if you multiply those elementary matrices on whatever matrix, that will do the corresponding row operation. So you can just have a string of elementary matrix that do row operation for you, like this. And then we can have the equivalence system written in terms of matrices. We have the equivalence of matrices that get the matrices you got by applying a whole bunch of row operation. And then we talk about singular matrices. So singular matrix, once again, is a matrix. A matrix is singular if you cannot find its inverse. And so in other words, it's non-singular if you can find the inverse. And then we have those three equivalence conditions for singular or non-singular. So in terms of non-singular, it's non-singular if Ax equal to 0 has a unique solution, and if and only if Ax equal to 0 has only the trivial solution, so a unique solution, and if only if A is row equivalent to I, identity matrix. Okay. And here we have an example of seeing this in other way. So if A is non-singular, sorry, A is singular, so A has no inverse, then X equal to 0 will have non-trivial solution. And I guess I made a mistake here. So A, never mind, yeah, non-trivial solution. Yeah, and or A is not row equivalent to identity. And if only if A is not row equivalent to identity. And here is an example of singular matrix. It's not invertible because it is 0 here. Okay. And so that's a quick review of this time. Any question? And yeah, and we have a lot of definitions. So like this upper triangular, lower triangular, or diagonal. But it's mostly just definition. Okay. So yeah, I guess that's 1.5. We have elementary matrices and using them to describe singularity of matrices. Okay. If no question, we are going to 1.6 that actually doesn't have anything to do with 1.4 or 1.5. It's a pretty simple, I guess, combinatorial fact, such that so this is this 1.6 is only talking about matrix multiplication. Okay. So there is something interesting combinatorially we can say matrix multiplication. So a matrix look like this. So it's a 2x2 block of numbers, and you can section those 2x2 block into whatever smaller blocks, right? So you have one big block here, and you can draw whatever some horizontal lines, some straight lines, and say you draw 2 lines here, and then you partition your matrix into 4 blocks. So we call this C11, and this C12, C21, C22. So C11 is a 2 by 3 matrix, C12 is a 2 by 2 matrix, and 2 by 3, 2 by 2, etc. Okay, and and another example, maybe you have a matrix P here, and you can partition it into you draw 2 straight lines, and you partition into 3 3 by 1 matrices. Okay, so and because each matrix is just a column, and then we can think of them as column vectors. Okay, so we can partition matrix into blocks, or partition them into or if your block is just columns, then we can think those blocks are column vectors. So you can think this matrix is just listing column vectors. Okay, and now we are just drawing lines, and how is this useful? Well, it's useful in that sometimes when you do matrix multiplication, so important thing is we are doing the multiplication here, right? So we are multiplying two matrices, and sometimes the partition can match up. Okay, then you can think about this multiplication as a different part of the partition multiplying each other. Okay, so for example, if I multiply A and B, you can think of it as A multiply with this B1, B2 to BR vector, so like this. And the multiplication result is just A multiply on B1, and so that's a vector, then that's a column vector, then on the second column you have A multiply on B2, and A multiplied by BR, etc., all the way to A multiplied by BR. Okay. And I guess let's see this example. Okay, so I should just copy B here. Okay. Anyway, so we have this example of A being excuse me. A is 2 by 3, and B is 3 by 3, and okay, so this is annoying. So B is like this, and 3 by 3, and we have B1, B2, B3, right? And then this is just some geometric thing about the matrix multiplication rule, right? So you see A multiplied by B should be it should be a 2 by 3 matrix. Oh, we have it here, right? Yeah, A multiplied by B is this 2 by 3 matrix, and we can see that the first column of A times B only depend on the first column of B, because so this number is this row times this column, and this number is this row times this column. And the other interpretation we have is that this column is a linear combination of those three columns, and with coefficient on B1. And this column is a linear combination of those three columns with the coefficient being B2, etc. Okay. So anyway, you see those three columns only depend on, so the first column only depends on B1, and the second column only depends on B2, and the third column only depends on B3. So you can see when you partition B into those three columns, then the corresponding multiplication of A times B also has those corresponding three columns, and the first column only depends on first column of B, second column only depends on second column of B, third column only depends on third column of B. So this is AB1, and this is AB2, this is AB3. Okay. And yeah. And more generally, okay, so this picture actually says, okay, so I should draw a picture to match this. So this picture here actually says what we want to say about this section. Okay, so we are multiplying a n by n matrix with a n by r matrix, okay, and n by n, and n by maybe r is really large, r, okay. So n by n, and n by by R. Okay, so then we will have and remember, so for matrix multiplication rule to work, you only need this n and n to be the same number, right? So this n and this n must be the same number, otherwise you cannot do matrix multiplication. So when we partition, then the only thing we need to care about is we need to matrix n and n. So you can partition this n equal to whatever partition you want, maybe 3 like this. Oh, sorry. I think, okay, don't want to risk it. Maybe this. Okay. And yeah, so you can partition this n equal to whatever partition. Okay. And then you need to have a matching partition on B. Then you can still do multiplication, and you can then multiply this m to do whatever partition, so whatever maybe squiggly line, and those are into whatever partition, and then you can then you can still do the multiplication by matching the corresponding partition the submatrix. So what I mean is, so you want to do a matrix multiplication rule of row by row, right? So then you can have the resulting matrix. Yeah. So the resulting matrix should be m by r. Okay, so m by r, and the resulting m by r will have the same partition on M and the same partition on R. And this block will follow the matrix multiplication rule. So you are just thinking about those block matrix elements. So this block will be this row multiplied by this column, etc. So this row will be 3 matrix. So you will have maybe I'll draw. So this one, this block matrix multiplying this block matrix, then this multiplying this, then this multiplying this, and adding them together, then will become this block. And you can check that all the dimensions should match, etc. Okay. Okay, so that's basically this section. So we can go home now. But let's see more example of this. Okay, and so this A times B is one example. This is where you don't partition A anymore, but A in any way. But you partition this R equal to columns. Then you got this A multiplied B example here. Okay, so you partition R equal to columns, then you see this AB has R partition into columns. Okay. And yeah, and another example of this is you think about B being identity, then you just have those standard basis vector picking off every column of A. Okay. And let's see another example. So this is an example where we don't partition B in any way, but we partition A into columns, and then we see that we can multiply each columns independently. So the AB can also be partitioned into columns, and the first column will correspond to first column of A. So this will be basically a linear combination of the columns of B. Okay, so this is so maybe it's hard. Yeah, so like this column should be twice of this column plus 5 times of this column. Let's check one number. So 2 times 3 and 5 times minus 1. So 1 plus 4. Yeah, so 6 minus 5. Okay. You can kind of see. So 2 will multiply on all those 3 numbers, and 5 will multiply on all those 3 numbers, and together become this. Okay. So yeah. So you partition, so you, yeah, so just as we said, we had an example of we partition R into 2 columns, and we had another example of partition M into rows. Okay. So the n and r partition are kind of arbitrary. And yeah, then here we have more cases. Okay. Yeah. Okay. So I guess those cases are not. Yeah. Those cases are really just separating what we draw into different cases. So into subcases. So first we are partition here. We have an example of partition B into just two sections. So this is like separating the R equal to two sections. Then when you multiply A and B, then you can check carefully with the numbers, but you see that will be A multiplied by on the first block and A multiplied on the second block. And as we say, we can partition A equal to rows arbitrary, the M partition M arbitrarily, so you can have arbitrary partition of those rows, and you do the multiplication, then the multiplication will have the corresponding multiplication of corresponding partition on the rows. Okay. And yeah, here we are kind of doing an example. We partition A equal to every rows, then we kind of group them together and think about those rows as A1, those rows as A2, and you see that you have the geometric thing that is this A1 part of the rows only depend on A1, and this A2 part only depend on A2. Okay. Yeah, the proof is really intuitive, so let's just skip the detail. You can kind of feel it yourself, or you want to be really rigorous, you can write down all the coefficients and then see the coefficients work out. And then we have case 3. Okay, case 3 is where we actually partition the middle part, but we are the book is written in very complicated notation. So, but I think the only important thing here is, okay, it's really complicated here, but the important number here is, so we are partition the n, the middle part, and so the only important thing is the middle partition need to match each other. Okay. So we are partition n equal to s and n minus s, and s and n minus s. So those need to match, and anything. So well, we're not doing other partitions, so it's whatever. And yeah. So we are saying this n is partition to n and n minus s, and this n and n minus s, and as long as those numbers, these partitions match, then you can do the multiplication. And just as we say, so you do the multiplication just like a matrix multiplication, and with each element being actually another matrix. So you have A1 multiplied on B1 and A2 multiplied on B2. And I guess here you need to be a little careful because, yeah, you just need to remember ordering. So remember, matrix multiplication are not commutative. So those elements here are still matrices. So when you do multiplication, you just need to be careful about don't mess up the ordering. So here we have A times B, so all those should be A something, then B something, A something, and B something. So the order doesn't change. Okay. So remember the ordering here. Don't change it. Ordering matter. Ordering. Careful. Okay. So we are thinking those are kind of matrix with scalar element, but you need to remember that they are actually matrix elements. Those are sub-block of matrices. Okay. And yeah, then finally we have case 4. So it's just basically doing all three previous things together. So you partition every part, and just need to be careful that this partition. So once again, the n part where you actually go through the multiplication. So those things should match those things, and the other partitions are arbitrary. Okay. and but it's really cool. So you can see that you can review those sub-block of matrices, kind of like just element of matrix. And okay, so we have a weird derivation in the middle, but whatever. Let's just see the result, it's easier. So you see that this is just like a matrix multiplication with every element being a matrix. So this block will be this first row times this first column, so A11, B11 plus A12, B21. And so like this block will be this row times this column. So A21, B12 times plus A22, B22. And but here once again you need to remember the ordering, because AB not necessarily equal to BA. So this is A11 times B11, not B11 times A11. Okay. So yeah. This is basically what we do in this chapter. Any question? Okay. Not this chapter, this section. And obviously here we are just sectioning into 2 by 2. But as we say, you can separate into whatever partition, as long as this partition on rows equal to this partition on columns. So you can match up this multiplication rule, because you want 2 things here and 2 things here, so you can do this addition. Okay. And yeah, here we have a higher example, but well, I think this is less intuitive. So as we say, we can partition into more blocks, and then you can just do matrix multiplication on those blocks. So like this C11 will be this first row multiplied on this first column, etc. Okay, yeah. So then we see more example, because why not? So A and B, and so here is we already partition B into this 2 by 2 block, and how can we section A into similar block to match this? Well, then as we said, the only important thing is this this partition. Yeah, this partition on column need to match the partition on row. Okay, so the only important thing is excuse me. So this partition on column, this partition, the partition on rows, yeah. So this partition on the row dimension, so actually a partition of column. Okay, so this is a very confusing notation. Sorry. So partition on the sorry, I'm confusing myself a little. Yeah. Okay. This partition on the column dimension, which is partition into different rows. Need to match this partition on the row dimension, which is partition into columns. Okay, sorry, it's a very confusing name I'm giving, but it should be clear intuitively. So this partition should match this partition, and the other thing is whatever. Okay, and so if you want to matching partition of A with B, then you need to at least partition A into the rows of A equal to 2 plus 2. The length of row equal to 2 plus 2, or the number, yeah. And anyway, so it's this partition must have, and the other partition is whatever. So we can have multiple solutions to have a matching partition. So here is the example. So you have the middle one, and then here we get the extra one, so we get some square, whatever. Okay, and you see that you can have A and B and those 4 blocks, multiply those 4 blocks, and you will have yeah, and you will have this resulting partition. So this one will be this matrix multiplied this matrix plus this matrix multiplied this matrix, And yeah, because it is row dimension 1 matrix, so resulting is row dimension 1, and etc. Okay, and another example, so you still have the middle partition, and maybe you want to partition in the lower one, so it actually looks like 2 by 2 blocks, and then the matching result will be this. Okay. And you see it's really the same thing, you are just drawing this line into partitions if you write out all the elements. Okay. And okay, then we run another example. Okay, so this example is even easier, but it's actually kind of important. So it's a special case of, let's say, I guess this is a little more than partitions. So if your A is already in this form, so when you do some whatever partition, and your A has this particular form, right? So A has this. So here in this example we have 2 by 2, and but you can really easily generalize to like n by n partition. Right? So if your A has this form where the of diagonal blocks are 0, then this is called block diagonal. And this is really nice because, so for example, we are okay, so we are proving something else here, but you can see, so we can multiply block diagonal matrix with block diagonal matrices, and obviously have a matching dimension. Then basically each block are separate, so you are just multiplying this block on this block and this block on this block, and you can multiply a lot of them. So if your matrix you can turn into block diagonal, then it's actually like 2 separate matrices, and in like independent dimensions. Okay, so that's useful in a lot of places, but we probably won't cover. But something nice to know. Okay, and anyway, let's back to this case. So this block diagonal matrix, we say we can improve a little thing on it. So this block 2 by 2 block diagonal. So I guess let's back to the digression a little more. So as we say, this block diagonal matrix can be more general, and it can be more general, and sometimes we can have like we have A1, A2, and A3, Okay, you can have those kind of block diagonal, and everything else is 0. Okay. So that's block diagonal matrix. But anyway, so here we just want to prove something simple. So we want to say A is non-singular if only if both of those are non-singular. Okay. And okay, so as we said, this is if only if you want to prove to the direction. So if both of them are non-singular, then they have inverse, and we can find inverse of A by just this matrix. Okay. And so we see that A11 minus 1. So we take the inverse of A11 here and the inverse of A22 here. And when you do matrix multiplication rule, you find out that this block is just, okay, so it's this row times this column. So it's just A11 minus 1 times A11 is identity. And similarly, this is the identity from A22, and so we got identity. And then you can check it out. Right inverse actually left inverse also. Okay. So yeah. So by construction, so we have a constructive proof that it's non-singular because this is A minus 1. Okay. And and then if A is non-singular, okay, so here we can okay. And okay, so we say then there is A minus 1, and we write this A minus 1 in block diagonal. And let's see what happens. So this block diagonal times your A should equal to identity. And so when we multiply this out, and that should be B11 on A11, B21 on A11, and this B12 on A22, B22, A22, etc. And anyway, so the off-diagonal are kind of not important, but what we need, off-diagonal are not really important because you can just say that these are 0 and doesn't matter. Okay, so if we are being a little smarter, then we can just say this as 0 because they are going to become 0 anyway. Okay, so we can say this as 0, 0, then this will be 0, 0, etc. Okay, so this is 0, 0, 0, 0 because you want it to be 0. And anyway, so the important one are these B11 and B22, and we see that B11 times A11 equal to identity, and B22 times A22 also need to be identity, and so this B11 and this B22 must be the inverse of A11 and A22. So both of them have the inverse, and so as we say, both of them are non-circular. Okay, so that's block diagonal matrix. Any question? Yeah, and I think that's it. So we should go to chapter 2. Yeah, only 30 minutes now. Okay, and anyway, so here is the review. Oh, I should. Okay, I will copy it up later. Yeah, as we say, we are basically just partition A, B into whatever. So what we are thinking here is we are doing A times B. Okay. So we are thinking about A times B and partition A, B into things. And as we say, we can. So A has n by n dimension, and B has n by r dimension. And you can partition those n and r into whatever partition, and also partition those two n into the same partition. Then you can kind of do this block multiplication. So here is an example of so you partition into a whole bunch of block matrix, and the matrix multiplication can be viewed as how do I say? You are doing regular matrix multiplication on those block with element being those block matrices. So for example, this element is the first row and times the first column. And remember, the ordering should not be changed. Okay. So yeah, that's block multiplication of matrices. Any question? Otherwise, so that's chapter 1, and let's try to go into chapter 2 then. Oh, actually, oh shit. I lose all the. Okay. I lose all the handwriting. And anyway, let's go into chapter 2 a little bit. Okay. Chapter 2. Here. Okay. Okay. And we only have 15 minutes, but I guess we can go through the most important part of this chapter. So we can, okay, so chapter 2 is determinant, and I think you probably learn a bit of this in high school also. But anyway, we'll do from definition again. Okay. So what's a determinant? A determinant is okay, we didn't actually say, but it's a number. It's a it's a function you can calculate on an n by n matrix. So it's only defined on n by n matrix, and it's called well, obviously determinant, and we use this notation data. It's a number. Okay, so it's a scalar. Okay. And it's very useful about matrix. But okay, so it will tell you a lot about the matrix, but the most important thing is it will tell you where the matrix is non-singular. Okay. Non-singular. Okay. This is a big motivation we care about. Okay. And we didn't say, but I guess we can say here for now. So basically, we'll see the determinant if a or equal to 0 if only if a is singular. Okay, that's the most important thing. First, one of the most important thing, and the second most important thing is how you actually calculate the determinant. Okay. And anyway, so other than delta A, we sometimes also want to write A in those express those element form. Okay, so this is the algebraic notation for determinant for us. And if you want to write down all the numbers, then the notation is this vertical line with your numbers. Okay, so determinant we written as so this block of numbers, your matrix, and then we sandwich them with a vertical line, and that's the determinant of A. Okay, and let's see. Do we have okay. I guess let's see an example here. I guess a small review. So determinant of A for 2 by 2, if you remember. So this 3, 4, 2, 1 is you think about basically all the permutation of the element. But anyway, for 2 by 2, we just think about this 3 times 1 and 2 times 4. Okay, so this is 3 times 1 minus 2 times 4 equal to 3 minus 8 equal to minus 5. And we don't have a room. Okay, 10 minutes. So let's go to the more technical definition. Okay. So our definition is a little funny. So first we need to define. So the definition of how you calculate determinant is recursive definition. So here we first need to define a funny thing. Minor of okay, and okay, so here first we need to define the weird substrate matrix Mij that we didn't give a name for. Okay, and so we have so maybe let's go here. So we have whatever matrix Aij. Okay, so here is maybe n by n matrix, whatever, and you can pick out whatever ij. So ij is some I row and j column, and there is some element aij here. And so for those, for every ij, you can pick up weird matrix mij here. So this is like yeah. So this is a matrix corresponding to aij. And so this Mij is n by 1 and n by 1 matrix. So remember, A is n by n. And so whatever Aij, you can think about you pick Aij, then you delete its row and its column. And whatever matrix left over is Mij. Okay? So here we have multiple examples. So if Aij is here, then this matrix is Mij. And Aij is here, then delete this column and this row. And you combine those two together, you get Mij, and the Aij here, then you get Mij. Okay. So we have Mij, then okay, okay, then then we can have the definition of determinant. So determinant is defined recursively like this. So if you have a 1 by 1 matrix, then your determinant is just whatever matrix element you have. And if you have another 1 by 1 matrix, then you can, so you have n by n matrix, then you can define your determinant by the determinant of n by n minus 1 by n minus 1 matrices. So those Aij. Okay. So what's those Aij? So we are saying you pick the first row of matrix, and so there are those A11, A12, and A1n, and they have their corresponding N11 to N1n, and then you take the determinant of those N1j. Okay, so you go through those first row, and you have corresponding N1j, and those N1j are n minus 1 dimensional matrix. And then you say you adding up them together by with this weird rule. So you have A11, so you have Aij multiplied by Aij, sorry, small Aij multiplied by big Aij, where big Aij is minus 1 to the 1 plus j times the determinant of n1j. And so why is this rule complete? Because so this is a recursive rule, because so you want to calculate the determinant of n by n matrix, then you expand it on the first row, and when you well, those A11 to A1n you can just real, and those minus 1 to the 1 plus j you can just calculate, and then you have the determinant of those submatrices, and yeah. This is n minus 1 by n minus 1 matrix. So if you know how to calculate the determinant of n minus 1 by n minus 1 matrix, then you are done. And then you can reduce this to another expansion. For example, you want to calculate this, then you do another expansion, you get n minus 2 by n minus 2 matrix, etc. And all the way down to this 1 by 1 matrix. And anyway, we call this whole thing, so this minus 1 to the 1 plus j delta Nij as a cofactor, or this 1 can be changed, so actually it's Aij. So back to here, so this Aij is of minus 1 to the I plus j determinant of Mij is called a cofactor. And yeah, but just this definition itself is not complete because we haven't said what's the determinant. But anyway, yeah, so that's cofactor. And I guess I'll see an example. So why this gives us the 2 by 2 rule? So we expand on the first row, and so we have A11 multiplied by the determinant of its cofactor, and cofactor matrix. Okay. So the Mij is just this A22 matrix. Okay. So I have A11 times big Aij is determinant of this thing. Okay. So it's A22 times minus 1 to the 1 plus 1 is 1. And then we have the second one. So A12 times the determinant of this A21 is A21. And but now we have the minus 1 to the 2 plus 1, so it's minus 1. Okay. So we have A11 plus A22 minus A21 times A21. Sorry, A12 times A21. And yeah, so this probably match the so this match the thing that you learn in high school. Okay. And and then we see that actually we say we expand on the first row, but actually you can pick any row in the column to do this cofactor expansion, and it will give you the same result. So we had our expansion of the first row here, and you can also expand on the second row, so it's A21, and multiplied by this big A21, which is just A12 with a minus 1, and then we have A22 times this big A22 is just A11. Okay. And also you can similarly check you expand on the columns and it will give you the same result. Okay. And then we see that we have a 3x3 example, and so you have this A11 times this cofactor, this big A11, which is this matrix, then then this 5 here multiplied by cofactor, which is determinant of the submatrix is 3, 5, and 2, 6, and this 4 times this matrix. Okay. And yeah, then you can calculate those determinants and get the result. And also, yeah, and also you can expand on the first columns, get the same result, etc. And I guess a little digression and the review is this is equal to, probably in high school you learn that. Oh, sorry. Probably in high school you learn that you want to do. Okay. Hopefully this is not confusing, but they are all the same because this is this line times how do we draw it in high school? Probably like this. So determinant of like these 9 numbers equal to so there are 6 possible permutations here. So you have like this line, and so let's have this. It's hard to draw. So, but hopefully this is a review. So you have this line plus this line plus this line, and minus and a nice lot this line, and plus this line plus this line. Okay. Maybe if I okay, this is a little confusing. Okay, but maybe if I just say it here. So yeah, so in high school you probably learned that determinant of 3x3 is 6 terms. So you have this element multiplied this element multiplied this element plus this multiplied by this multiplied by this plus this multiplied by this multiplied by this. Then subtract from this multiplied by this multiplied by this, and this multiplied by this multiplied by this, and this multiplied by this, and those 3 multiplied together. Yeah. So it's all possible permutation of the ordering. I guess all possible permutation of elements where the row and the column number doesn't match. Doesn't collide. But anyway, this is a definition that we will not use in this class, and just hopefully this will remind you of something you learned in high school, and you can check yourself that this definition is the same as this cofactor expansion, but in the following, we'll just do everything in terms of cofactor expansion. So use the cofactor expansion as the definition of determinant, and we'll derive all the property of determinant with it. Okay, and yeah, I think that's for today. And so once again, we'll homework on chapter 1, and next time we'll tell you more about determinant. Okay, see you next Monday.